got to do a little bit of background sciencey stuff first. So we want to talk about the basis the basics. Think science. How many of you here have had a chemistry class or physics class at some point? Yeah. Atoms and molecules. What are they made up out of? So if I look at an atom, this atom's going to have a nucleus, and at the nucleus there's going to be some protons, some neutrons. I'm just making up my, look like that. We'll go with it. You may remember what a proton and a neutron are? Little subatomic particles. Most importantly for us, protons are positive. Neutrons, well, term neutral. They don't have a charge. This forms my nucleus. Out around the outside, we have our electrons. This is a classic Bohr model of an atom. Don't worry, you will notice I have no periodic tables up on the walls. There's a reason for that. Okay. We're not a science class. Well, we're an engineering class. But our basis is science, and we just need to always keep track of what's going down at that basic level. What holds my atom together? The attracting forces between positive protons and negative electrons. That's what bonds them together. If you do a chemistry class, you start talking about different atoms combining to form molecules. Why? Well, they want to share electrons with each other and feel a little more balanced with things. An electron and a proton have exactly the same charge. It's called an electron charge because it's the smallest charge there is in the universe. There's nothing smaller than an electron that has charge. So it turns out that anytime I talk about charges, it would be some even multiple of electrons or protons. They're very small, so we don't usually think of it that way, but they really are. It's just so many electrons. There's no space between them. If I measure that, we'll talk a little bit about this unit. Unit of charge is a coulomb. Now, electrons are very small, so they're like 1.6 times 10 to the minus 19th power coulombs. So very tiny. We just want to think about what's going on with these electrons and protons that make them do the various things we need them to do at a little higher level. And it always helps to step back and go, oh, that's what's happening way down at that science level. Well, that's what's happening on that periodic table. If you take a look at your periodic table, it has, it kind of looks like this. I know there's, again, I've been in chemistry since I was 18, so go with my periodic table. But it has a bunch of columns in here. There are numbers in there. The numbers tell us, this isn't the right number of columns, but the numbers tell us what? They tell us the total number of protons at the center of this. So it's all about electric charge. Everything we have in this universe is about electric charge. Everything's built out of bonds of electric charge. What holds everything together to make the Earth? Well, all these atoms are held together with other atoms to make molecules, to make bigger objects, which are all just these really strong forces between electrons and protons doing things. Now, we don't usually talk about it for that. Why? They balance each other out for the most part. If I look at this, I've got 4 negative charges and have 4 positive charges. So there's really strong attractive forces hold them together, but they don't get outside of it. It's neutral. It's just total positive, total negative, I would say. If you look down here in this first column, so I'll go back and test. I know all of you talked about it, even if you haven't had a chemistry class. Somewhere in physical science, but it might have been like 9th grade. You talked about this. You have what's called electron shells. That are where these electrons are. You picture them as like these little spherical shells around the nucleus that go out. Actually, that actually builds back to this charge, only having discrete charges, so I don't have in-betweens. That's actually based on the energy levels that they have to form those. Like you can't be between those orbital areas. They're either in one or the next. Kind of seems counterintuitive at first. All right. Now, this first column, if you go up and down it, has 1 electron in that outer shell. Anybody remember the term for the outer shell? It starts with a V.
Valence.
Yeah, valence. Be on the first test, right? No, that's chemistry. But valence. So that valence shell is just the outer one for it. You know, you're up here with hydrogen and it has 2 possible electrons in its valence shell, but only has 1 because it's just a hydrogen atom. If I get below that hydrogen and down in here, I don't know if you remember what kind of materials these are. Those are all metals as a whole. Now, why do I want to talk about those? Well, they have that 1 electron out in that valence shell, which means it takes very little energizing of that electron for it to go, you know what, I don't have energy, I'm going to hop over to the next atom. And it gets over there, and that atom's got extra electrons, so that electron takes some of that energy and just jumps over to the next atom. And it just keeps going. That forms something I'm going to call a conductor. I'm guessing you've heard the term before when I say conductor, electrical conductor. Maybe not. When I say that, does it make you think of anything? Watch me on close. Make you think of anything. What? When I say electric conductor, what's your first?
Like copper?
Yeah, copper, metal.
Electricity.
Yeah, it carries electricity, allows electricity to flow through it. So, electric charges flow through a conductor. Why? Well, because when you form up copper, steel, silver, aluminum, gold, all those really common metals that we think of, they have typically 1 electron out in that outer valence shell, and it's not tightly bound to anything, so it can very easily carry some energy. We can get charges moving because why? Because the electrons have charge. I mean, that's the basics of it right there. Electron gets some energy, hops over to the next atom, and they start hopping and they just kind of flow along. My electrons are flowing through this conductor very much like water would flow through a pipe. Yeah.
Is it only conductive if it has less electrons than protons?
No, they have the same number.
They have the same number.
Yeah. Yeah. When you get into your textbook, there'll be a nice table. Again, it looks like it was made in 2003, but it's all right. It's not, at least it's not 1963. It's a free text. But it has a whole list of conductors. You're going to notice most of them are metals. Most of them are things that naturally in nature carry electrical charge. They allow electrons to flow through them readily. There will be a list then of everything else. There are some things that are quite either one, but as a whole, most things are conductors or insulators. Insulators. What do insulators do?
Do they keep the electricity bound?
Yeah, electric charges do not. By the way, my writing never gets bad. Let's just say it this way. If you ever have an issue reading something, pass. I tried to stay neat. What I find is actually there's more fatigue to this than you might think after you go through 2 or 3 of these a day. So sometimes it's like, so ask. Yeah. Most things in nature are an insulator. Electric charges don't readily flow. That may not even be because they, at certain stages, atoms might well charge to flow. But let's just think of something. I'm going to give you an insulator here that you may not think of as an insulator. Water. Don't stand in the water with, the blow dryer, right? That's true. Why? Because water holds lots of ions inside of it. Ions are things that have one less electron or one more or even more. So they have charge in them, those ions. Water naturally pulls things away. So it's dangerous thing. But if you have distilled water, so with none of the ions on it, it's just pure water, it's an insulator. Has 2 hydrogen atoms, which would each have an electron in the outside. Has looks like a donut, but that's an O inside. Oxygen atom, which has 6 electrons. It has spots, if you remember this back in chemistry. For 8 electrons out here in the valence shell, they have 2. So what do? They share electrons. They're tightly bound. A little water molecule, if it was all by itself, or with all other water molecules and none of those suspended ions that exist in all the water we deal with day to day. It's an insulator. It's not going to conduct electricity. Why? There's nowhere for these electric charges to really flow because all those little electrons are tightly bound. Okay, I've said this. I will now remind you: do not go home and stand, in the bathtub with the toaster because I said that. Only if it's distilled water and you have no air around, nothing to pull off particles. But so lots of polymer type insulators. Rubber is a natural insulator. I mean, most things are wood. Now, a couple things that are non-intuitive with this, though. My conductor stays neutrally charged. I have to put a lot of work in to electrically charge a conductor. So my conductor allows charge to flow through it because it doesn't hold the charge. I have to isolate it so it has nowhere for the charge to flow and then jumps through some hoops. Why do I not want to grab the copper wire? Not because it holds the charge. I don't want to grab the copper wire because it lets the charge readily flow right through it into you or me. Insulators. Insulators can hold a charge. Why? Because the charge can't flow through them readily. Let's give you a real quick example here. Everybody done the balloon where you rub it on carpet or something and get some friction on, you stick it in your hair and it pulls up. Why? Well, that frictional work transfers electrons from one object to another, so now the one with extra electrons on it has a negative charge, so it's charged. The one that lost depends on what material you have, by the way. The one that loses the electrons has a positive charge. But there's nowhere for those charges to just flow around it. Otherwise, if you're holding that balloon, they would just flow up through you. They'd be safe. They flow up through you and disperse and be neutral. They don't. They stay charged. Or you do the same thing this time of year. If you have your socks on your carpet floor and swoosh across the floor and touch the dog on the nose or whatever. So don't encourage that. But why your socks, especially if you have wool socks, but cotton do it too. They're insulators. You're shuffling along. You're transferring electrons back and forth, so you end up with a shifting of charges around. It's just actually because you're moving electrons from one to the other through that interaction. So one thing ends up positive, one thing ends up negative. Anybody, we used to do this like middle schoolers. You take like a glass rod or a rubber rod, use faux fur, you used to use cat fur, but some sort of fur, you get that frictional. One of them ends up positive, one ends up negative. You get that charge, so not. All right, I mentioned this because, well, these are just, this is probably maybe counterintuitive. Holds a charge, neutral. I got a question for you. I have conductors and insulators. Most things are conductors or insulators. Actually, most things are insulators. There's quite a few natural conductors. Most of the conductors are metal, not all of them. Anybody have, there's a third type of material. We use it in every single thing, every day in the 21st century. But it's not either one of those.
It's like a battery.
Batteries are not, but this is a good question. Yeah, I know what you're saying.
Semiconductors?
Yes! Is that what you said too? See, that's because you're sitting in the back. I know both of you are. For those that arrived late, I made fun of them because they came in and I think the back 2 rows were full. I think one of you were sitting in the second. I really don't bite. I don't think. Maybe. Do I bite, John? Yeah, semiconductors. So they're exactly what they say on the tin. Semi, half conductor. Half the time they're conductor. Or part of the time. They do occur in nature. We're mostly semiconductors. Carbon's a natural semiconductor. We don't use it much. Most things we use, most of our semiconductors are silicon. Hit Silicon Valley, silicon wafers for computers, phones, microcontrollers throughout, whatever, you have like 50 microcontrollers throughout your car now to control everything. All those are made out of semiconductors. Everything you might think of as computer related, or however you want to parse that term at this point, is a semiconductor. We will talk about them a little bit this semester. We couldn't do things like amplifiers and stuff without them. I should say modern amplifiers. Before semiconductors, we had 50 years of amplifiers without them. Anybody happen to know what those are? Here, I'll test history here. Most electrical engineers probably. Vacuum tubes. Anybody heard of a vacuum tube? How many guitar players in here only use a vacuum tube amplifier? Yeah. They're not semiconductors. They look like light bulbs rolled in vacuum with electrodes inside. Okay. We are done with the science portion of this. I will have, and the homework, I'm going to ask you a little bit to look up some stuff on electrons and protons and stuff. I'm okay with, I'm going to go look it up. Why am I making you do that? Just so it informs you, connects you a little bit. Okay, back in whenever, 9th or 10th grade, we covered this, and I realize now that this is not something brand new. It's building off of that. It's a practical application. So my electrons are flowing. In my conductor. All right, we need to talk about